The use of drones is quickly spreading in the society. When equipped with cameras, these drones can become great cinematographic devices and can be used to create complex and compelling motions. However, precisely controlling the motion of these cinematographic drones remains a challenging task, especially when filming moving persons. In this paper, we propose to encode cinematographic knowledge into drones and then offer a control of high-level properties to the users, letting them draw camera trajectories that avoid obstacles, control the framing of targets, and orchestrate the behavior of multiple drones. To build such a system, we proposed a dedicated model to control a drone in relation to targets, a path planning technique that generates collision-free paths while enforcing smooth and feasible trajectories for the drone, and a method to orchestrate the motion of multiple drones filming dynamic targets. Our first contribution is a parametric camera space dedicated to cinematographic drones, which prevents the camera from colliding with the targets, encodes visual properties over targets, such as external or apex shots, and ensures the drones can move to any configuration in this parametric space. Our second contribution is a dedicated path planning technique that computes cinematographically smooth paths between two drone positions expressed in our parametric space, when ensuring their feasibility by the drone. To this end, we build a sphere-based roadmap representation of the collision-free space. In this example, we move from current drone position to a desired drone position by planning a path through the sphere-based roadmap that avoids collisions, ensures continuity in cinematographic properties, and is feasible by the drone. To evaluate continuity in cinematographic properties, we compare our approach with a user controlling a drone using a joystick, the manual flight mode. The bottom curve displays the top view trajectory, and the curves on the right display the evolution of target positions on screen, scale or size of targets, and orientation of the camera. The lower the value, the closer to the desired drone position. We then compare this manipulation with Oskam's viewpoint transition planning technique that does not ensure continuity in properties. Blue graphs show important variations, and as you see, the camera loses the targets a couple of times. Our approach, now displayed in red, maintains the screen positions, top graph, smoothly transitions from one shot to another, mid-graph, and smoothly changes orientation, no fast or sudden changes in camera angles. Our dedicated path planning technique can also be used to quickly sketch drone trajectories in a top view by planning a feasible drone path that fits the user's input trajectory, in red, while avoiding obstacles in the scene, the white circles. The user can specify the height of the drone and view the framings along the path. The path is then computed automatically, in yellow, and the drone can perform the motion here in a virtual environment. We now illustrate the process with a real drone. The user sketches a spiral motion around a target. This is a motion that is difficult to realize manually with a drone. The computed trajectory in purple is then executed by the drone in the real environment. Interestingly, the path planning technique can be used to maintain visual properties on moving targets while avoiding static obstacles. Here the camera needs to maintain the target at the center of the shot with a given size. In addition, the obstacles can be dynamic. Here, a second character is trying to block the drone from moving to its target position. As you can see on the left, the trajectory in purple is automatically recomputed to avoid the obstacle. Finally, our system proposes a mean to orchestrate the motion of multiple drones on moving targets in a way to cover alternate viewpoints on the scene, in the same way a film crew would do. The master drone, drawn with a blue wedge on the top view, first maintains a medium shot on one character and then on the other. The second drone plans a path to cover an alternate view on the scene while avoiding to be seen in the view frustum of the master drone. As the characters move around, the properties are sometimes difficult to maintain. A way to avoid this would be to rely on anticipation strategies, one of our next research topics. The remaining of this video is composed of footage taken during our experiments with novice users. Do note that the drones we used were not equipped with gimbal cameras nor stabilizers.